It's undeniable that AI currently has a profound impact in our daily lives. We're experiencing lots of changes in education, in healthcare services, and even in the way we do our jobs. AI is being currently used for high-stake decisions such as guiding drug discovery process and pretrial detention and release. Therefore, due to the key role played by these AI models, there are lots of ongoing research efforts in an attempt to make these models fair, fast, and accurate. At this point, you may be asking yourself, how can we make these AI models even better? I'm Fabricio Murai, assistant professor with joint appointments in the computer science department, data science program, and affiliated to the recently launched AI program. In my lab, we design new models using data coming from digital platforms, which often manifest themselves as graphs or networks. Data from digital platforms have been used for decades by computational social science to better understand society and the impact that those platforms have on us. And don't be mistaken, these platforms have been using AI trained on their own data for quite some time to rank, make predictions, and recommendations. Now, however, after large foundational models trained on data coming from digital platforms have caught the public interest, like ChatGPT, studying AI models and trying to provide certain guarantees has become even more important than ever. In my lab, we design fairer, faster, and more accurate AI models based on a multi-pronged approach. I will talk about three aspects of this approach in detail. The first aspect concerns capturing invariances that are intrinsic to the data. An invariance is simply a property that does not change with a given transformation. For example, let's say that I pass an image of a cat to a classification model that distinguishes between cats and dogs, and the output is cat. Now, if I apply a transformation that shifts the image a little bit, ideally, the output of the network must be exactly the same. Mathematically, if the input is denoted by x, the transformation is t, and the model is represented by a function f, I want f of the transformed input t of x to be the same as f of the original input x. This is approximately true for convolutional neural networks and explain why they are so powerful when working with image data. Therefore, one of my research interests is to learn models that can capture invariances that are present in the data. In particular, for graph inputs, where the goal is to predict the property of a graph, the output should be the same, regardless of the order in which I index the nodes. You don't want, for example, a model that classifies as a molecule as toxic or safe to humans to give different outputs when you permute node indexes. Therefore, models that capture invariances are more accurate, but also easier and faster to train. Here are two examples of graph data sets that my collaborators and I collected and have worked on. So the first are networks based on GitHub repositories, and the second correspond to social graphs that can be built from political discussions on Instagram and Twitter, for example. In addition to invariances that are common to all graphs, I'm interested in investigating whether we can learn additional approximate invariances directly from data. The second aspect that permeates my research is the use of multimodal data and multitask learning. Multimodal data consists of using different input types referring to the same object. For instance, a facade image of WPI's Boynton Hall and tabular data with information about the same building can be seen as multimodal data. While we cannot combine these informations directly, we can project them into a shared latent space and, using attention models, fuse them while determining which parts of each input are more important for a particular prediction. In turn, multitask learning consists of learning to predict multiple target variables jointly, which is especially helpful when these variables are correlated or when you don't have a lot of data. In our example, we can try to predict both building age and architecture style simultaneously. One very interesting example of multimodal data comes from clinical trials. Given a disease or condition, we are interested in determining whether a specific drug can be helpful to a population specified by a list of inclusion and exclusion criteria. In this case, the disease is expressed as an ICD code, which uniquely locates the disease in a particular hierarchy. The active ingredient in a drug, in turn, is a molecule represented as a graph. Finally, the criteria is essentially text organized as a bulleted list. In this problem, the goal is to learn better ways to fuse the data in order to obtain better predictions, whether the molecules are safe and whether they are effective against particular diseases. Last but not least, the third aspect concerns the mitigation of societal biases in the data. As I mentioned earlier, digital platforms' data reflect society and hence our own biases. Just as in the garbage in, garbage out principle, when AI models are trained from biased data, they will be inherently biased. Using such models can only exacerbate disparities and perpetuate existing bias. Hence, detecting bias in data is a fundamental task for which I describe two applications. The first is the detection of biased medical information, which consists of incorrect health information that can prevent some individuals from getting correct medical treatment, oftentimes a minoritized group. Despite having been debunked, some theories continue to be taught in medical schools and disseminated online, like the South gene hypothesis that links being black with high blood pressure. In many cases, once you condition on the so-called structural determinants of health, such as structural racism, income inequities, the correlation between group membership and the disease disappears. In order to detect biased medical information online, we collect data from Twitter, train a model that filters the tweets that contain medical claims, and a second model to identify bias using our exclusive data set of annotated bias excerpts from medical curriculum. The second is related to health disparities experienced by historically underserved populations. Using electronic health records, we plan to incorporate structural determinants of health in order to identify biases in healthcare, which can manifest themselves as, for example, requesting different sets of exams or giving different prescriptions to two patients that, apart from the group membership, they exhibit the same risk for the treated condition. More generally, we aim to identify and alleviate societal biases in the data. If you found these research topics interesting, feel free to drop me a message on the email shown at the bottom of the slide.